chapter 2 here, and we were talking about really periodic trends is sort of where we left off. We talked about ionization energy there sort of last time. We're also going to talk about, again, as I mentioned, electronegativity. And really, a lot of the sort of periodic trends that we talk about here, a lot of it is sort of the basis for what we see happen when things really come together to make bonds and how certain elements will make bonds. Also, why certain elements maybe are more reactive than others, like we saw in lab the other day. So I also want to talk about another sort of aspect of sort of periodic trends, which is important, and it's what is sometimes referred to as effective nuclear charge, and it's sometimes referred to as Z effective. And the effective nuclear charge is really the positive charge that electrons feel based on really kind of their position near the nucleus and really the position of other electrons that may be sort of in front of them. We talked about the idea, I think, of sort of valence electrons versus sort of core electrons. Valence electrons, again, are the highest energy level electrons. They're really the ones that are involved in bonding, really because they're not held as tightly. And part of the reason they're not really held as tightly is effective nuclear charge. So if we look at something, say, like a nucleus that has 3 protons, which would be our friend lithium, by the way, and it's got 3 electrons, right? So it's got like a 1s2, 2s1 type situation happening there with our 1 electron there at the end being its valence electron. So when we look at sort of the interaction between those electrons and the nucleus, obviously we understand hopefully that opposites attract. So things, again, with opposite charges are attracted to each other. There's also sort of a level of strength in terms of that type of attraction. And what I mean by that is sort of the larger the positive charge, the larger the negative charge, they're actually going to hold each other a lot tighter than something with a smaller positive or negative charge. So if you're kind of comparing something that's like a +1, -1 that comes together versus something that's like a +3, -3 that comes together, the -3 and +3 is going to be held together a lot tighter through that electrostatic attraction than the kind of +1, -1 attraction. Now, as we talked about, electrons are moving randomly about the nucleus in a sort of a random pattern. They are sort of tied to the nucleus due to that attracted force between it. And again, that's back to sort of that like wave that's on a string. The guitar string can't really move away, is tied to the guitar. Same idea here with our electrons as well. So when we look at these lower electrons here, which are our core electrons, they are much closer to the nucleus, and they're really going to feel pretty much the full brunt of the +3 attraction from that nucleus. That means that they're really going to be pulled in pretty tight, and they are going to be held really, really tight because of that. When we get to our valence electron out there past that in a higher energy level, this electron actually experiences what is sometimes referred to as shielding. And shielding is pretty much what it kind of sounds like. Lower level electrons basically will shield the nucleus's positive charge, and it doesn't feel really the full brunt of that +3 charge. Kind of like when you go to the movies and you used to be able to pick your seats, I guess, before the assigned seats, but you get there early, you got a nice center seat, and then somebody comes right before with a big giant hat and sits in front of you, shields half of the screen and all that good stuff. So there's sort of the same idea here. These lower energy level electrons are going to kind of shield that full +3 charge. So you could actually calculate sort of the charge that that electron out there is feeling by taking the Z effective would be the atomic number or positive charge from the protons, which is +3, minus the number of electrons, which are essentially shielding it, in this case would be 2, which means instead of feeling a +3 attracted force to the nucleus, that outer electron is actually only feeling a +1 sort of attraction, which means it's not going to be held as tightly. And that's also why that valence electron is easily removed, involved in bonding. Because of that, it's not held as tightly. Also, why we talked about last time that it takes a lot of energy when you try to get to those core electrons, which are closer to the nucleus, because frankly, they're feeling the full brunt of that positive charge. They're being held very, very tightly. And under normal circumstances, you're not going to really pop those guys off or kind of remove them. Any questions on that there? Now, electrons in the same energy level, for example, these guys, they don't really shield each other because they're in the same energy level. So it's really just guys that are sort of in a lower energy level that will sort of actively shield higher energy level electrons. In terms of effective nuclear charge, essentially on the periodic table increases as you kind of go this way and decreases as you go that way. Increases to the right because frankly, as you go to the right, the atomic number increases, which means that positive charge in the middle is going to be much larger. And it's going to bring even those outer electrons in closer because of that stronger positive charge. Even with the shielding happening, it's going to be able to kind of drag everybody kind of closer to the nucleus. Any questions on that there? So last time we did talk about ionization energy, and a reminder that ionization energy is the energy that is basically required to remove an electron in the gas phase. When we remove an electron, what type of charge does that thing become? It does become positive charge. So when we talk about ionization energy, a lot of times we're talking about it in the sort of aspect of the formation of cations, which are positively charged ions. So obviously, a lot of times we will relate sort of the ionization energy to the formation of positively charged ions. And as the example we looked at last time, electrons are basically removed one at a time. And for every electron that you remove, there's a certain ionization energy associated with just simply removing that one electron. First electron would be the first ionization energy. Second would be the second, and so forth as you go down. And the general trend that we saw is it gets much, much harder every time you pull off an electron. As you pull off an electron, everybody kind of shrinks, which means those outer electrons have now just moved closer to that positive charge, going to be held tighter. In that case, going to require more energy. And at some point, like we see here, when we get to, say, the third electron there in magnesium, we have hit those core electrons, which once again have started originally closer to the nucleus and find themselves probably even closer to the nucleus as we continue to kind of remove those outer electrons. So again, that typically doesn't happen. As you can see by the energy demand here, it is basically a 10-fold difference there from removing the first one to trying to remove the third one. And that's a pretty big jump in terms of energy. In general, as we will see, ionization energy on the periodic table increases as you go to the right and up, and decreases as you go left and down. Again, right and up is pretty much where we have our nonmetals, and that is why nonmetals typically will, once again, kind of hang on to their electrons. Left and down on the periodic table, pretty much metals, which are typically the guys that will form cations and give away their electrons relatively easy. So in general, as we talked about, as you go across the period from left to right, the first ionization energy will increase, and it's because electrons are added to the same quantum level, do not really shield one another. So that increasing nuclear charge will cause those electrons to come in closer, and we have more protons that are being added. So the opposite is true, as we talked about. As you go down a group, we do see the first ionization energy start to decrease. And again, the electrons at that point are going to be further away from the atom. What happens as we add more electrons to an atom is, and as we go up in terms of energy levels, so for example, if we go left and down on the periodic table, we're like at period 6 or 7, right? That means that's really the 6th or 7th energy level, right? The principal quantum number. Orbitals are the same shape, right? But as you go from one energy level to the next, they actually get larger, right, to accommodate the extra electrons. So obviously, as we go down and left, we have a lot more electrons, orbitals getting bigger, which means, again, those electrons are going to find themselves actually further away from the nucleus because of that, and not being held as tightly as well. Also, because we're going to the left and down, you don't have as big of a increase in terms of protons as you do on the other side, to kind of bring everybody way down. So we do see larger size in that. The actual first ionization energy as we go across a period, as we can see here, it is definitely not really a linear relationship. And there are some few exceptions as we go through here. And it does have to do with electron-electron repulsion. So obviously, as we feel electrons right into these orbitals, they really, for the most part, don't want to be near each other either because they're negatively charged, but they really can't escape either. And that's why we do get sort of the differences in energy of the different orbitals that sort of happen as we continue to sort of fill electrons in there, because there is some of that. We're going to try to kind of get away from each other as far as we can, but obviously we can't completely get away from each other. Hence why, you know, for example, the 4s drops lower in energy than, say, the 3d, which is higher in energy, and they get those electrons first. And you don't have to worry about the actual exceptions to ionization energy. You just need to know, obviously, the general trend of how it goes on the periodic table, and obviously what ionization energy is. All right, so let's take a look at this. Which atom would require more energy to remove an electron, sodium or chlorine in this case? That is both answers. One of them should hopefully be right. All right, sodium's on the left. Chlorine's in the exact same period, we call that, right? Going across. So chlorine's further to the right of the periodic table, which means its ionization energy should be larger or smaller? Should be larger, right? And because it has a larger ionization energy, it's going to take more energy to remove an electron. So I would probably go with chlorine perhaps on that one. Yeah, would be the right answer there. Remember, the ionization energy is the energy required to remove an electron. So the higher the value, the harder it is, obviously, to remove the electron, and more energy is required to do so. Which atom would require more energy to remove an electron, lithium or cesium there? It would be lithium. In this case, they're both in the same group. So again, further up in the group would actually be higher ionization energy. Further down in the group would be lower the ionization energy. So in this case, it should be lithium, right? Now, which one should have a larger second ionization energy? Lithium or beryllium? Beryllium, okay. So let's take a look at it. Let's look at the electron configuration for lithium, which is 3, I think, still, right? 1s2, 2s1. Now, beryllium is 4 right next door, I think, and that is 1s2, 2s2. When we talk about the second ionization energy, that means which electron's coming off? The second one, right? So when I look at lithium, how many valence electrons does it have? 1 valence electron. When I look at beryllium, how many valence electrons does it have? So which one's going to be harder to remove the second one from? It's going to be lithium, right? Yeah, let me say that one more time. I think you're right, what you're saying there. So when I remove the very first electron from lithium, which would be my first ionization energy, that would be that guy, yeah? When I go to take the second one, I am now into what electrons there? Those are the core electrons, right? Which is like not going to happen without a lot of energy to do that. When I take away for beryllium, my first electron, we're going to come out of here, right? Which will still leave me 1 more valence electron, right? Which shouldn't be too much trouble to remove. So we could remove that probably a lot easier than dipping into the core electron that we have in the lithium. So in this case, after that big explanation, I hope it's lithium, there it is. So lithium would actually be the one that would take a greater amount of ionization energy because you have just dipped into the core electrons for lithium, but for beryllium, you're still hanging out in the valence electrons, which obviously would take a lot more energy than the first electron, but jumping to the core electrons for lithium would take a lot more energy than probably that second valence electron trying to remove from beryllium. Any questions on that one there? So here's a chart of some of those ionization energies. And again, as we travel that we looked at magnesium, a really big jump. When we look at sodium, after that first electron, you're into those core electrons, which is again, a very, very big jump. This is again why we really only see things make certain charges. So again, everybody in group one pretty much has one valence electron, which means not going to be terribly difficult to remove that valence electron. So they typically will make a +1 charge. Things in group two have two valence electrons. So again, going to take a little extra energy to remove the second electron, but it is doable until you kind of get to that third electron, which is obviously in the case of magnesium right about there. When we get to aluminum, it is okay to kind of get there to that third electron, but look at the big jump as you go from the third electron to trying to rip off the fourth electron, which is again why aluminum is pretty much a +3 situation that occurs at that point when you get into those core electrons. The general trend, as we see, this is going across a period here. And we do see going across the period, right? The first ionization energy increases as we get down to the non-metal section. When you look at the non-metal section, which is like here, they're starting out in the thousands to remove an electron, which is like what these guys do to get to the second electron. That's again why non-metals typically will not lose electrons, because just to try to get rid of those first electrons takes a lot of energy to do so, and they really don't want to do it in the first place. Any questions on that there? Let's talk then about, yeah. So they have on the left there that the ionization energy generally decreases as you basically go from right to left on the periodic table. Yeah. That's why I said it was increasing as you went that way, but decreasing obviously as you go the other way, which is what they chose to draw their arrow going the other way, that way. Yep. Other questions? Okay. The next sort of periodic trend is electron affinity. Electron affinity is really the energy change that occurs when an atom gains an electron, right? So when somebody gains an electron, they are going to become negatively charged. So we think about electron affinity with the formation of anions, which are negatively charged. And we see that reflected in this equation. Some element gains an electron, ends up with a negative charge. Electron affinity, if you have an affinity for electrons, pretty much what it means is like you like something if you have an affinity for it or you know how to do some things. So something that has a high electron affinity, they typically like electrons. And we typically will see a more negative sort of change as we go from left to right in terms of the energy value. And in general, the electron affinity becomes more positive as you go down a group. So the general trend for electron affinity, which is different than electronegativity, electron affinity increases as you go this way and decreases as you go the left and down. It is not a perfect trend, especially with the halogens, for example. It increases as you go up group 7, then around chlorine it drops, and then it goes back up around fluorine. So there's not a perfect sort of trend, but the overall general trend of the energy change that occurs as it increases up to the right and decreases down and to the left. Any questions on that there? That also relates to sort of the size, the atomic radius as we go from left to right on the periodic table gets a lot smaller. Again, we're building up a lot more positive protons as you go to the right, also electrons, which brings everybody closer in. The effective nuclear charge, as we talked about, also increases as you go to the right. So even those outer electrons, because of the number of protons there are in the atom, will still feel, even with shielding, a pretty good positive charge coming at them. So even though, you know, there are shielding happening as you go up and to the right, those outer electrons are still going to feel a pretty good positive charge, which is going to bring them in closer to the nucleus. And if my electrons on the outside get brought closer to the nucleus, the overall size of my atom then becomes smaller, right? And as the effective nuclear charge sort of decreases as you go left and down, that means those outer electrons are not going to feel as big of a positive pull in. So those outer electrons are not going to be pulled in as much. And that means the overall size, right, of our atom is going to be a lot larger. So in general, what we see is size decreases as you go that way and increases as you go left and down on the periodic table. In addition, as you go left and down, as we talked about a second ago, there's a lot more orbitals and a lot higher principal quantum number, again, going to sort of build out the overall size of your atom. Any questions on that? We did talk about, I think the other day, the idea between a neutral atom and an anion, which is negatively charged, and a cation, which is positively charged. With neutral atom becomes a cation. Is the cation larger or smaller than the neutral guy? It is going to be smaller. Once again, it is going to lose electrons, right? Which means its outer sort of electron cloud is going to shrink as it loses electrons. So the positively charged ion will be smaller than the neutral ion in general. And opposite is true in this case. As a neutral atom, obviously not the same one, but another neutral atom goes and becomes an anion or negatively charged, is going to gain electrons to its valence shell, right? The outer part of it. And that's going to increase the size. And the anion would be larger than its sort of neutral counterpart in general. Any questions on that there? Yeah. It's actually size. So it's actually what is referred to as the atomic radius. So like from the center of the nucleus, if you will, to sort of the outside of the electron cloud, that radius basically, if you want to think of like a circle, you know, kind of like the radius from the from the center to the outside. Other questions on that? And here's sort of a picture of that. And again, we can see up and to the right there, we're decreasing, left and down, we are increasing. So another important periodic trend that we're going to add to it is electronegativity. And electronegativity really is in chapter 3. So this is the only thing from chapter 3 that you need to know is about what electronegativity is and how it relates to the periodic trend. So electronegativity, which again is different than electron affinity. Electronegativity is the ability of an atom to bring electrons towards itself. So electron affinity is the energy change that occurs when an atom gains an electron. Electronegativity is basically the ability of an atom to kind of bring electrons towards itself to eventually probably gain or share electrons. So there is a slight difference in the meaning of those two. In general, on the periodic table, as you go up and to the right, it increases. As you go down and to the left, it decreases. The most electronegative element we have is fluorine. So fluorine is the most electronegative element that there is. If you look at the periodic table, fluorine is pretty much as far up and to the right you could go, except who's to the right of those of fluorine. It is the noble gases. Noble gases, as we talked about, are essentially chemically inert, which means they're unreactive, which means They're perfectly fine the way they are. They're not looking to trade electrons, give away electrons, or do anything. And as we talked about, as we'll talk about in the next chapter as well, the purpose of all bonding is for everybody to get there in terms of their electrons. So really, noble gases have no electronegativity. They really don't have any attractive forces to try to pull any electrons to anybody. So really, in the case of elements, fluorine is the most electronegative as far up and to the right as you could go. Any questions on electronegativity? So you do need to know what it is. You need to know the general trend. Now, if we look at all of our sort of trends here together on the periodic table, we see a couple of things. We see that as we go up and to the right here, our size gets smaller. Our size increases. As we go up and to the right, our ionization energy increases and decreases as we go down. As we go up and to the right, our electron affinity increases and then decreases as we go down. As we go up and to the right, obviously not drawn perfectly, our electronegativity increases and it decreases as you go this way. And all of these things, including up and to the right, our effective nuclear charge also increases and decreases as you go down and to the left. All these things and all these trends really help us understand what happens with different types of elements. When we go up and to the right on the periodic table, that is pretty much where we find nonmetals, right? Up and to the right. And what we see with nonmetals is they typically have very high ionization energy, which means it takes a lot of energy to remove an electron. That is because the size is really small. So even the outer electrons are being held a lot tighter to the nucleus. They have a very high electron affinity, which means they like to gain electrons. And not only that, they like to bring other people's electrons towards themselves because they have a high electronegativity and they have that high effective nuclear charge, which brings everybody in really tight. All of those trends leads to what we know happens with nonmetals is they are typically the ones that want to gain electrons. They definitely don't want to get rid of their electrons. Going pretty much to this side of the periodic table, where we have metals, going left and down, we have a much larger atom to begin with, which means our outer electrons are not going to be held as tightly, which means it has a low ionization energy, which means you don't have to do a lot of convincing to remove an electron. They have pretty much low electron affinity and low electronegativity, which means A, they don't like to gain electrons, nor are they interested in bringing electrons to themselves. And they have that lower effective nuclear charge, which is pretty much going to allow those outer electrons to kind of hang out there and be willing to be given away. And that's typically what we see with metals is they typically are the ones that will lose electrons and become obviously positively charged, while these guys over here obviously become negatively charged. Any questions on any of those periodic trends? Yes, and how they relate? So that is also why the basis of an ionic bond happens, because you take a metal that has all those opposite periodic properties and a nonmetal that's on the other end of the spectrum, and the metal goes, go ahead, take my electron, and the nonmetal goes, thanks, I'll take it, no problem. That is the actual conversation they have with each other, and the electron actually transfers from the metal to the nonmetal. That is also why we have covalent bonding, where we don't have transfer of electrons, because in covalent bonding, everybody's hanging out in the same location on the periodic table, which means we have nonmetal and nonmetals that come together. And both nonmetals are pretty much of the opinion, I like electrons, I like to hang on to my electrons, And the best that they could do is, all right, you can't take it, but we'll share. So we'll do some type of sharing with the electrons. And as we'll talk about in the bonding chapter, that sharing may be equal sharing or it may be pretty unequal sharing, but there's some aspect of sharing happening because neither one of them wants to lay up the electron and pretty much give it away. They both really want to hold on to electrons and bring electrons to themselves. Any questions on that? Also explains a couple of things that we saw in the lab on Tuesday. When we did the halogens, the most reactive halogen would be which one in group 7? Out of the ones we did, it was chlorine, and we estimated that probably fluorine was even more reactive. And that makes sense as well, because fluorine is right up there, top right. That's your center of, I'm taking electrons, bring me electrons, right? When you looked at the metals, I think we did magnesium and calcium, maybe, yeah? Between magnesium and calcium, which one is more reactive? Calcium. Calcium is further down, right? Coming down and to the left, which means pretty much take my electrons, please, right? Not a problem. I'm going to be ready to react. So that's why we see those reactivity trends that we saw in that experiment, because as we went up and to the right, we're going to see more reactivity of our nonmetal. Most reactive nonmetal would be up to the right in the corner. Most reactive metal would be lower left of the periodic table because of these periodic trends. Any questions on that? All right, I might have answered a post-lab question maybe as well as we're up there. All right. All right, so let's see here. Which one should be the larger atom, sodium or chlorine? Should be sodium, further to the left. Again, not as large of a Z effective there, so spread out a little bit more as we go to the right. Again, those outer electrons are going to be pulled in tighter because of that greater positive charge. Which one should be the larger one here, lithium or cesium? Should be cesium. Again, coming down, we're increasing the principal quantum number, increasing the size of the orbitals, going to keep bumping out really those electrons further away from the nucleus. And even though it has a little bit greater of a positive charge, there's a lot more electrons further away to start with. So it's not going to feel as much of that effective charge to bring it back in. So we're going to see cesium being a larger atom. Which one is larger, the hydrogen 1s orbital or the lithium 1s orbital? So it is going to be, I will answer this question too. All right, so I heard lithium for the larger orbital, 1s orbital. How about which one is lower in energy? It's like a 50-50 shot. Could really only be wrong twice if you guess twice. Obviously, if you guess two different things, but if you guess the same thing twice, maybe you can be wrong once. I don't know. So, all right, so let's start with the first one, right? So hydrogen is obviously 1s1, right? It's got one electron, one proton. Lithium is 1s2, right? 2s1, right? All right. Positive charge on the hydrogen is what's in the center there? What is the positive charge? +1, yes. Positive charge on lithium there is going to be +3, right? All right. Which one will be larger in this case? It is going to be the hydrogen, right? And that's because this positive charge, right, is a +1 to +1 -1 attraction, right? That's a +3 to kind of +3 type of charge. So that's going to be pulled in a lot tighter to each other, which means the overall size of this guy is going to be smaller, right? So it's going to have a higher effective nuclear charge in that case, right? There is no shielding happening in this case, right? So that is not going to be pulled in as much And this one is going to be, again, sort of larger because of that. The one is lower in energy is actually the lithium one, for what I think I said a second ago. I meant to say that for the energy. Because of this positive 3 charge, it has a higher effective nuclear charge. So it is going to pull that 2s orbital in. And obviously those 2 electrons that are right there in front of the +2 are going to be pulled closer to the nucleus in this case. So it would be the lithium 1s orbital. So for lithium, it's 1s orbital, or these 2 electrons, which feel the full brunt of this +3 charge. Greater positive charge going to bring the 1s orbital closer in. Remember that the higher the positive negative charge attraction, the stronger it's going to be, as opposed to hydrogen, whose 1s orbital is going to feel only a +1 pull in, so it's not going to be pulled in as closer. The result of this hydrogen not being pulled in as closer, since that's the only electron there, this will be a larger overall size because it hasn't been pulled in as close to the nucleus. Because the lithium gets pulled in closer to the nucleus, that's going to make everybody pull in tighter, right? And overall is going to be actually smaller, the overall size. The actual energy of those 1s orbitals, the lithium is going to be pulled more closer to the nucleus than the hydrogen because of the +3 versus +1 charge. Yeah. Yeah, so yeah, that's basically how positive negative attraction works. The larger the charges, actual number of those charges, the stronger that attractive force is going to be. It's kind of like a magnet, I guess, right? If you had a really big magnet, like that's the positive charge, it's gonna kind of pull that whatever is attracted to, like the paper clip in really tight. If you had like a weaker magnet, like the +1 charge, right? It's going to kind of pull it in, but not as tight and as close as it would in that case. Other questions? All right, range these in order of increasing ionization energy. Oxygen, fluorine, and sulfur, which I think that is the answer, what we have up there. So let's take a look at it. We have location on periodic table. We have oxygen, fluorine, and then sulfur is right there below it. So in terms of ionization energy, it increases as we go up and to the right, which means these lowest ionization energy should actually be sulfur, right? Because it decreases as you go down. So sulfur would be the lowest, followed by oxygen, which is in the same group. And then fluorine is further to the right. So sulfur, oxygen, fluorine would be the increase in ionization energy. Increasing size would go opposite. Remember that up and to the right, things get smaller and larger as we go down. So smallest guy here would be fluorine, and then next smallest would be oxygen next to it, and going down below oxygen would be larger, which would be sulfur. Any questions on that there? All right, so I believe we talked about the periodic table right there today with the groups. Did we officially talk about the periodic table? Groups and metals and that? We did, right? All right, let's just make sure. I don't know. All right, that's the periodic table, just to make sure. All right, good talk. I like it. So one reminder, just to make sure, I don't know, I teach 5 classes. I've talked about the periodic table somewhere along the way in the last 3 weeks. But a reminder that when we talk about groups, we do use the representative numbering, usually in chemistry, which is the A numbering. There's also B numbering, you sometimes see, and no numbering, just 1 through 18. Like I think that's what they have up there going on. Most of us use the A numbering in most chemistry classes, and most people don't call it A, they just call it group 1, group 2, group 3. Groups go up and down right on the periodic table. So group 1 is right here. It actually starts with lithium, not really hydrogen. Group 2, we skip the middle. Group 3, 4, 5, 6, 7, and 8. Right around here at boron, there's usually like a staircase that kind of works its way down there on most periodic tables, as you can see. To the left of the staircase, those are metals, which are obviously very good conductors of heat and electricity. They can be hammered into sheets, pulled into wires. They're usually shiny in appearance. These guys on the bottom are also metals. Up and to the right of the staircase are our nonmetals. Nonmetals are pretty much the opposite characteristics. They are dull, they're brittle, they're used as insulators. They also have a much different variety of states. So a lot of nonmetals are gases, solids, and liquids, as opposed to metals. Most metals are what? Solids. Most metals are solids. The one exception is mercury is a liquid. That's why it's blue on most periodic tables, because it's actually a liquid. At the staircase, which is like silicone, arsenic, all those guys kind of coming down this way, these are what are referred to as semi-metals or metalloids. And semi-metals or metalloids are pretty much elements that have characteristics that are very similar to metals, and the same element has characteristics that are also very similar to what you find in nonmetals. And that makes sense if you think about where they're located. They are pretty much metals. And then as we come up, we're transitioning really into nonmetals. So they're almost like the transition point between metals and nonmetals as you go up into that case. Now, some groups have special names. And the first group, which is group 1, is the alkali metals, which again starts with lithium, not hydrogen. That is because hydrogen is what type of element? Is it a metal, a non-metal? Just if you're not sure, let me tell you, hydrogen is a non-metal. Yeah. Even though it's hanging out over there with all the metals. So that is why hydrogen is not part of group 1, because group 1 is all metals that start with lithium. Hydrogen's over there because it has unusual properties. If you're old like me, they used to print periodic tables and they would put hydrogen on both sides right next to helium as well. You don't see that too often anymore. People do that, but hydrogen is actually a non-metal. A lot of non-metals are those diatomic molecules like H2, N2, O2, F2, Cl2, and so forth. So group 1 is the alkali metals, lithium, sodium. Group 2 is the alkaline earth metals. Group 7 are our halogens, like we did in the experiment the other day. So again, that's a lot of those diatomic guys, F2, Cl2, Br2, I2, fluorine, chlorine, bromine, iodine. Group 8 is our noble gases, which is our helium, our neon, argon, krypton, xenon, all the ons are over there in our noble gases. As we talked about, noble gases again are chemically inert. They really don't react with other things, but they will react with themselves. Between group number 2 here and group number 3 in this region, those are our transition metals. Transition metals typically can have multiple types of charges, as we'll talk about when we talk about naming. These two groups on the bottom are the lanthanized and actinized, which a lot of radioactive elements are found down in this region. If you follow the numbering, as I think we talked about when we talked about sort of electron configuration and counting off on the table, if you follow the numbering, these two rows actually kind of go like right in there. And those are also why they're sometimes referred to as inner transition metals, because they actually do go sort of with the transition metals at that point. Alkali metals, alkaline earth metals are where a lot of strong bases come from. The word alkaline means basic. So sodium hydroxide, potassium hydroxide, calcium hydroxide. If you kind of come this way and add some hydroxide to those guys, OH minus, you get a lot of the strong bases that we come across in chemistry here. Periods obviously go left to right on the periodic table. There are 7 periods, right? Starting with up here, 1, 2, 3, 4, 5, 6, and 7. So periods go left to right on the periodic table. Obviously, things in similar groups or periods have similar sort of properties and similar periodic trends because they're located in the same spot on the periodic table. Any questions on any of that there? So there's our division of our periodic table. Since we're talking, and we'll be talking obviously about bonding and things making charges. Typically speaking, do things have charges when they are just by themselves off the periodic table? They do not. So things don't actually have charges if they are uncombined off the periodic table. So if you have just a piece of zinc metal, it has no charge. You have hydrogen by itself, it's just hydrogen gas with no charge. Things only really do gain charges when metals and non-metals come together, and that's when things actually will make charges. So when things make charges, typically everybody in group 1 will make a +1 charge. Everybody in group 2 will make a +2 charge. Aluminum is usually what we're talking about right about there. We'll make a +3 charge. Our nonmetals above the staircase, starting in group 5, will make a -3 charge, -2 charge, and -1 charge for group 7 there. Once again, up and to the right, non-metals going to gain electrons, so they're going to be negatively charged. Obviously, our metals on the other side will be positively charged. Transition metals, which are again sort of in this region here, can have multiple types of charges, but there are 3 exceptions to that, and the 3 exceptions is zinc and cadmium. Those guys, when they make charges, will always make a +2 charge. If you hang a left from cadmium to silver, it will make a +1 charge. So in the transition metal region, those 3 are sort of exceptions. They actually have fixed positive charges, those 3 guys right there. That's a good thing to remember. Any questions on that? Is there a good pattern for group 4? There's really not. It's kind of right in the middle of the metalloids and all that. Also, in this region below the staircase, these are metals or non-metals? Those are metals, so they actually have positive charges. So those are things like lead, right? Tin, which is SN. They also, although they're not technically transition metals, can make multiple types of charges as well. So those guys can have multiple charges as well. All right. Any questions on periodic trends, periodic table? This is chapter 2, I think. Yes. So once again, the only thing for chapter 3 you need to know at this point is what electronegativity is and how it relates to the periodic trend. We obviously will talk a lot more about electronegativity in the next chapter, which is bonding and how it relates to bonding. But for exam 1, this will be all the material